Now, a processor or microprocessor, or sometimes people call CPU, right? That tends to be a central component in most embedded systems. Strictly speaking, you don't necessarily need a processor. You may have used FPGA in some of your courses. Have used PLA, PAL, or some of the programmable logic, or you may have seen gates, AND gate, NOR gate, OR gate, some of these, right? You could build an embedded system in those terms, in hardware components. But that's not what people tend to do today, unless that's something very specialized. I'd say 99.999% of the cases you use a little processor, or actually a microcontroller, which is a special form of a processor. Okay, so what does a processor do? Well, it executes instructions from program memory. And what's an instruction? Well, an instruction has what's called opcode and operands. Opcode is basically a representation of what it's supposed to do. Could be to do addition, subtraction, multiply, divide, shift bits. It could mean control. And control in this case actually means jumping. You could make an unconditional jump from one memory location to another location, or it could be conditional. That is, you test the condition to see if you want to jump or not, right? And then load and store instructions. These, what they do is they bring in memory content to the processor, or they write data from the processor to memory. Okay, so really these are the three kinds of instructions that a processor tends to do, and so basically it just your computer just executes instructions and then transform data. Right, that's really what a processor does. Now, so here we're talking about memory, but there could be program and data. Now, program and data may occupy the same memory or may occupy different memory. Okay. There's also things called microcontroller units or MCU. You'll see this term over and over again. And an MCU is really what most people use in building embedded systems. Rather than just a plain processor, they like to use microcontrollers, which are microprocessors enhanced with input and output capabilities. Okay. Now, so there's input and output interfaces, which we'll talk about in the next couple of weeks. In addition, there's also memory built in. See, for most general purpose computers, memory tends to be a separate unit, a separate component or separate module from your processor. For most microcontrollers nowadays, almost all of them have built-in ones. Now, you also see microcontrollers, really high-end ones, that need much, much more memory. So what they do is they do stacking. So they take the memory and then stack on top of the processor. And so it looks like one chip, but then if you take a closer look, oh, okay, there's layers, and they're stacked. Now, there's different kinds of memory, of course. There's SRAM, there's flash. And then for input and output, it's not just digital input and output. There's also analog signals. So there's ADC and DAC for analog to digital converter and digital to analog converter, right? Some may have voltage comparators and so forth. A major trend that you're seeing in the past 10 years or so is this trend towards integrating network interfaces and even radios onto the same chip as the microcontroller. So see, these tend to be, or they used to be separate chips. Now they're all part of the same chip, and that's pretty powerful. And that's a major trend we're seeing in the past 10 years. And what's going to happen in the next 10 years? I think even more integration. You'll see maybe integration of additional sensors, additional devices, larger memory, and so forth onto the same chip. Okay, but in any case, a microcontroller or MCU is really the central component of most embedded systems. So we'll spend several weeks just to talk about the different features of microcontrollers. Now, so how does a microcontroller perform I/O, or input and output? So there are two styles, and you can see the explanation in the textbook as well. There's one style called memory mapped I/O, another style called ported I/O. And these two styles are also still very common even today. Memory mapped I/O means, well, you have a memory space, no matter how big it is, right? Just space means the range that you can address, because to access memory, you have to provide an address. Now, how big is that space? Well, it's 2 to the power of number of bits, right? So if your address is 16 bits long, how big is the memory space? Well, it's 2 to the power of 16, right? Which is 64K. Now, if you have a memory address that is 32 bits, then how big is the memory space? It's 2 to the power of 32, which is 4 gigawords, right? And a lot of times the unit of word is a byte, so it's 4 gigabytes. Now, just because you can address a large enough space doesn't mean you actually have that much memory, right? Your actual memory can be less than the space you can address. Does that make sense? All right, so just because you have a processor that uses 32-bit address doesn't mean your computer has 4 gigabytes of memory. You could have 2 gigabytes. You could have 1 gigabyte or less, right? So the space is just the number of distinct locations you can name. But just because you can name an address doesn't mean there's actually the storage location there, right? You can have maybe only 1 gigabyte of memory installed. And so if you say, I want address at the 3rd gigabyte, well, there's no memory there, sorry. So that could happen, right? So that's the difference between address space and actual amount of memory. Now, memory mapped I/O works because it's assuming, well, the address space is larger than actual memory you ever have. Especially for embedded systems, that tends to be true. Because if you take a look at little EcoBT that we have, right? I've shown a couple of demos with this one. Its address space is 2 to the power of 16, right? 16-bit address, so that means it can address 64K bytes. But if you take a look at the spec, it only has 8K of actual memory. So that means 64 minus 8, 56K is not real memory. That's just addresses, right? And same thing with like ARM. ARM architecture tends to be 32-bit addresses or 4 gigabytes of space. But if you get a microcontroller that's an ARM, chances are you're not going to get all 4 gigabytes of memory that comes with it. That's just too much. So that means there's a lot of unused addresses. So what memory mapped I/O does is to say, well, these are empty locations anyway. Let us do mapping from those addresses to input and output devices. And that's how it can address those devices, right? So it names those devices by mapping the devices to certain address ranges. And then each address may correspond to a different operation. So that's what memory mapped I/O does. So you then do reading and writing to those memory locations, and that triggers I/O to happen. That means you might be, so for example, if you want to receive a packet from Ethernet controller or send a packet to Ethernet controller, then with memory mapped I/O, you might say, oh, I know this memory address corresponds to the Ethernet controller. Then I just keep writing to this address or keep reading from that address, right? So that's one way to do it. Now, ported I/O is a different style. Basically, it uses a different address space for what's called special function registers. And so this way, you can have clean separation between input and output action from your memory access. So that way, your entire memory space is available for actual memory. And to do input-output, you have a different set of instructions that access a different memory space. And those addresses then cause input-output to happen. And those are what's called ported I/O. And in this class, since we're using the 8051, it actually uses ported I/O. But we'll